For topic 3, we're going to look at solving trigonometric equations where we can use reciprocal functions. So we're still going to have the same issues that we had in topic 2, where maybe our argument is or is not alone. So there's going to be actually one of each here. But we can use a reciprocal function to make life a little bit easier. Okay. So remember your reciprocal functions. The reciprocal of sine is cosecant. The reciprocal of cosine is secant. And the reciprocal of cotangent is tangent. And we tend to like those, like especially sine and cosine, because those we can go directly to the unit circle and they're like easy values to see. Tangent's a little more work, but we're good. We got this, okay? So example 5 says solve each equation, finding all solutions from 0 to 2 pi. Okay, so first we have secant of 3 theta divided by 2 equals -2. Well, we know secant has a reciprocal function in cosine. So I could instead solve cosine of 3 theta over 2, but it has to equal the reciprocal. So we want to make sure that when we solve the cosine function, we set it equal to the reciprocal of -2, which is -1/2. Okay, now let's talk about cosine of 3 theta over 2. That is really the same thing as cosine of 3 over 2 theta. So we essentially have 1.5 times theta. So we know that when we're dealing with y equals cosine of omega x, if omega is greater than 1, we have a compression to our period, which means this the cosine function is going to cycle more frequently from 0 to 2 pi. And then if omega is less than 1, it stretches out the period, which means cosine is going to cycle less frequently. It's going to cycle less than one full cycle from 0 to 2 pi. So essentially, this means cosine cycles 1.5 times from 0 to 2 pi. So we need more than just 2 solutions. Okay? So we already know what happens if we have cosine of 2 pi. We ended up with 4 solutions. That happened in the previous video. Here, we're not going to have 4 solutions. We're actually going to have 3. So we're going to have like the typical number of solutions on, like if you look at the unit circle, all of our trig ratios, they repeat. So you're going to see them all twice from 0 to 2 pi. So if we have just theta, we're going to get 2 solutions. If we have 2 theta, we're going to double our solutions. If we have 3 over 2 theta, we're going to have 1.5 times the normal value or the normal number of solutions. So we're essentially going to get 3 solutions here. But let's go ahead and just play. We're not going to look at the graph initially. We're going to solve this one and then we'll look at the graph at the end. Okay? So we're going to go ahead and let u equal 3 theta divided by 2. So then I'm going to replace my argument 3 theta over 2 with just u. So I'm looking for cosine of u equals -1/2. So we can jump over to the unit circle and we can say, okay, when is cosine equal to negative, was it -1/2? Yes, -1/2. So we'll go to our unit circle. It may have drawings on it from the previous video. It does. So let me erase this junk. Well, I don't really have to erase that, but I'm elbows deep. Okay, so we want to know, when do we have a cosine ratio of -1/2? So cosine, remember, is always the x coordinate on these points on the unit circle. So we have cosine of -1/2 at 2 pi over 3. And then we have cosine is -1/2 at 4 pi over 3. Okay, so let's go back here. And we're like, okay, so u is going to be 2 pi over 3 and 4 pi over 3. But we know those 2 solutions aren't going to be enough. We're going to need more, okay? So what we can do is we can go ahead and find another cycle of solutions, okay? So we can look for 2 plus 2, or u plus 2 pi. So if I have 2 pi over 3 and I want to add 2 pi, I need to find a way to write 2 pi where it has a denominator of 3, but it's an equivalent statement. So that would be 6 pi over 3. So I have 2 pi over 3 plus 6 pi over 3. So that's telling me that we're also going to look at 8 pi over 3. And then we're going to do the same thing for 4 pi over 3. We're going to find an angle coterminal to 4 pi over 3. So we're just going to add 2 pi to that. So 4 pi over 3 plus 2 pi is going to be 4 pi over 3 plus 6 pi over 3, which is 10 pi over 3. Okay, so we have one full cycle, and then we have 2 full cycles. We're not going to need all of this, so we may have to do some We may have to do some fancy work here in just a minute, okay? Now, at this point, we can go ahead and say, okay, we know that u is equal to 3 pi over 2, so let's set each of these equal to 3 pi over 2. So I have 3 pi over 2, not 3 pi over 2, 3 theta over 2. Please make sure you write that as theta. Gracious. So we have 3 theta over 2 equals 2 pi over 3. We're going to have 3 theta over 2 equals 4 pi over 3. So we're taking all of these values for u and setting them equal to 3 theta over 2. So then 3 theta over 2 equals 8 pi over 3. And 3 theta over 2 equals 10 pi over 3. Now don't freak out. We know the condition on theta is that it has to be between 0 and 2 pi. These two are for sure bigger than 2 pi, but it doesn't matter because they're u. Okay, so let's go ahead and solve for theta in each of these. So essentially what we're going to do, okay, when we divide right here, when we divide by 3 over 2, it equals multiplying by 2 over 3. Please make sure you understand that because we don't always have time to go through this. So we essentially divide both sides by 3 over 2. So I get theta, and that's going to equal 2 pi over 3, but I want to do the reciprocal of 3 over 2. So I'm going to multiply by 2 over 3, which gives me 4 pi over 9. And I'm going to do the same thing over here. I'm going to divide both sides by 3 over 2. That's going to give me theta equals, well, 4 pi over 3 needs to be divided by 3 over 2, which means I multiply by 2 over 3, which gives me 8 pi over 9. And we repeat the process. So we divide both sides here by 3 over 2, which is going to give me theta. And then 8 pi over 3, I need to divide it by 3 over 2, which is the same as multiplying by 2 over 3. So I get 16 pi over 9. And then we want to do this one more time. So I divide both sides by 3 over 2. So I get my theta alone. But then I need to divide 10 pi over 3 by 3 over 2, which means I multiply it by 2 over 3. So I get 20 pi over 9. Now, we have 4 values for theta now. So we can say, okay, theta is now 4 pi over 9. 8 pi over 9, 16 pi over 9, and 20 pi over 9. But we need to make sure all of these are between 0 and 2 pi. Well, 4 divided by 9 is less than 2 pi. 8 divided by 9 is less than 2, which is less than 2 pi. 16 divided by 9 is less than 2, and so we get less than 2 pi. But 20 divided by 9 is more than 2, so this one doesn't work. Okay, this one is outside of that domain restriction that we initially set for theta. So that kind of makes sense. We know one full cycle of cosine would give us 2 solutions, but we need 1.5 cycles of cosine, and that gives us our 3 solutions. So this is our solution set from 0 to 2 pi. Okay, and if we were to graph this, we want cosine of 3 theta over 2 equals -1/2. If I were to graph this, I would graph cosine of 3x, good grief, x divided by 2. And I want it to intersect y equals -1/2. And so we can see that we have 4 pi over 9, 8 pi over 9, and 16 pi over 9. And this is again from 0 to 2 pi, so you could see that that 20 pi over 9 would have been outside of the 2 pi range, okay? And if we want to be like really thorough, remember the original graph that we had was secant. So we had secant of 3x divided by 2. And it needed to intersect the line y equals -2. And it does at 4 pi over 9, 8 pi over 9, and 16 pi over 9. So you can see here that we proved that the reciprocal functions, we're going to get the same. We're going to get the same values for theta. Okay, so let's go back to the worksheet. Luckily, the next one that we're going to look at, we have theta by itself, so it's not going to be as bad. Okay, so for part B, we have √3 times cotangent of theta plus 1 equals 0. So let's go ahead and solve. We want to isolate the cotangent. So I'm going to start by subtracting 1 from both sides. So I get √3 times cotangent of theta equals -1. And then I want to divide both sides by √3. Okay, so that gives me cotangent of theta equals -1 over root 3. And I'm going to leave it like this for just a second because cotangent, I mean, there's nothing wrong with cotangent, but we're really comfortable with sine and cosine, and then we're pretty comfortable with tangent. So let's rewrite this as tangent. So use tangent instead. Okay, so when I do that, I can say, okay, well, tangent of theta, I can solve for that, but I don't want it to be -1 over root 3. I want it to be the reciprocal of that, which is negative root 3. Okay, and we already know that tangent equals sine over cosine, and we can get the root 3 when cosine, no, when sine, oh, please do there we go. And this occurs when sine is the root 3 over 2. So just keep that in mind. That's our little trick there. Okay. So if we go to the unit circle, we need to find where tangent is equal to negative root 3. Well, tangent is always going to be a root 3 ratio when cosine is 1/2 and sine is root 3 over 2. But we need to have a negative relationship, so we need one to be positive, one to be negative. So it's going to happen. Let me erase all this crap so we don't. I shouldn't say the word crap. That's rude. Let's erase all this other stuff that I had. So we know that we're going to get negative root 3 at 2 pi over 3, and then we're going to get negative root 3 at 5 pi over 3. Okay? So let's see. So we get 2 pi over 3 and 5 pi over 3. Let's go back to the worksheet. So theta equals 2 pi over 3 and 5 pi over 3, okay? And that's basically it. That's our solution, right? So we don't really have to do anything else because we had the theta all by itself, so we didn't have to do any weird work there, okay? So there you have it. If you wanted to look at this on Desmos, you could. I think for the sake of this video and the length of this worksheet, we're not going to, but you could graph tan x and then y equals negative root 3, or you could graph cotan x and y equals -1 over root 3, and you'll see those two solutions pop up. Okay, so that is what you do when you have a situation where you could potentially use a reciprocal function. So if you have secant or cosecant, it's really nice to use sine or cosine. It just makes things easier. And with cotangent, I think it's really nice if we become very familiar with tangent and then we can use that to our advantage. Okay.